Thank you. This next one is just a high-level ideas talk. I just want to make a case for what I call mixed abstraction HDLs and then discuss various implementation details regarding HDL design. So first, let me give a quick high-level overview of HDL abstraction levels. So we have like these event-driven abstraction languages, so things like Verilog, VHDL, or the behavioral subset of LLHD. The primitives here are kind of like digital state and event-triggered updates and like delays, so like actual time-level delays. And the domain here is some type of continuous time. It's not strictly continuous, but we have a very fine discrete notion, and 2-4 valued signals are common here. And the utility of this abstraction is like behavioral modeling of mixed signal or digital IPs and also RTL design. But only a subset can be mechanically translated back to hardware. The next kind of going up the stack of complexity of abstraction level is the register transfer level. And this is a subset of what you can describe using a generic event-driven abstraction. And so there's many examples here. I think most of what we work on falls in this category. The primitives are like flops and SRAMs and also like the operations we use to connect them. And the domain here is now like very explicitly discrete time, and usually there's a notion of like a continuous fixed frequency clock. And the utility here is obvious. This is like synchronous digital circuit design, what we're very familiar with. Going one level up, we have these like data flow HDLs. So these are things like defined or TL Verilog or pipeline C. And the primitives here are kind of like token streams. There's notion of like ordering and various operations, and then there's some like data flow state that you maintain as you shoot tokens through a particular block. And the domain here is kind of like a tokens in, tokens out. This is very like abstract, but bear with me for a bit. The utility here are for these like data flow circuits. So many DSP circuits fall in this category. In addition to that, having like some kind of automated pipelining support. All of these languages support something to that extent. And then going up a little bit more, we have these like what I call lightweight HLS abstractions. So this includes things like Calyx IR or XLS. The primitives here are, again, like digital states. We have imperative control blocks similar to the recipe blocks that I showed you earlier. And then scheduling is something that can be done either explicitly or implicitly by the compiler, and then binding is something that the compiler usually takes care of in doing resource allocation. So the domain here is like the control block statements kind of are the granularity at which you process updates in a lightweight HLS language. And the utility here I think is very nice. It's like this controllable HLS where we have explicit state, and then we have a way for the user to guide the optimization that the compiler uses to generate the hardware. And then finally, we have the last category, which is this heavyweight HLS category. So this includes things like LegUp or Vivado HLS or Catapult. And the primitives here is just, it's almost the entire language of System C or C++, some subset of it. The domain is usually transaction level, so we're dealing now with like things that go into a port and then things that come out of a port. And the utility here is like mostly automated state control construction and optimization. So there are pragmas, there are ways to control this, but by and large, this is like a monolithic tool that just takes a blob of C code and tries to turn it into RTL. So I want to note, like, we have this emerging world of multiple abstractions. So circuit now has multiple dialects. So we have like the RTL type dialects, we have data flow level dialects, we have lightweight HLS dialects. And there is a desire among hardware designers, I think, to use like a suitable abstraction level when designing a given hardware block or a given hardware model. So I propose here that like we should look into how we can design these mixed abstraction HDLs. The current situation is that each of these dialects is kind of isolated for both simulation and design, but it's possible for us to define some interaction semantics between them. And also HDLs only target some specific dialects right now. So trying to mix abstractions isn't really well supported outside of just a black boxing approach. And I try to say that this next iteration of HDLs, we should try to support mixing abstractions in the design language. So how does this potentially look like? So when trying to mix like RTL and higher level abstractions, transaction level modeling and latency insensitive interfaces are kind of a canonical solution to this like integration question of how these two things should talk to each other. But when we go to like a much finer design granularity where we want to like use lightweight HLS where we're kind of in line with like data flow type DSLs along with like RTL DSLs kind of in one module, and now it becomes very difficult because typically we want to share state between like these RTL and higher level descriptions. And currently there isn't a good way to specify how to do that. The other note here is that we can have much better simulation performance if we simulate the parts of the circuit at a high level of abstraction differently from those at a low level. So that's something to keep in mind as well. So the other thing is we want to go kind of underneath. So we want to start off with RTL and try to mix in like these event-driven abstractions. So many of these like common circuit constructs like clock generators or muxes or async resets are much easier to describe in like an event-driven paradigm versus as RTL like blocks. And I think we can look at Verilog scheduling algorithm to provide kind of a starting point for how we might try to mix these like gate level and evented blocks. Again, this is not something for which I have a concrete idea, but I just want to propose this as a question we should be looking at. And we need to consider like how do these abstractions interact with each other even when they cross multiple levels. So we want to be able to take very high level abstractions and maybe compose them with like event-driven abstractions. That might be difficult. And finally, we want to ask ourselves like what is the API that hardware designers actually want? So for what circuits is what level of abstraction most useful? And I think this is something we still don't have a very clear view of. So in my last 2 minutes, I just want to discuss some one slide each other implementation questions for HDLs that I think we should investigate. So one question is like, which primitives actually belong in an IR or HDL? So one common issue is you have specialized SRAMs or CANs in a given process. Now, how should we model those? Should they be modeled as primitives in the IR? Should they just be regarded as black box things that can only be simulated in Verilog simulation? Or should we try to model all the intricacies of these things inside the HDL IR itself? And this also goes to the second question, is should these PDK primitives be directly representable or should they be black boxed? And I think right now the answer is, well, they're black boxed, but maybe there's a better way to do this. The other issue here is that of preserving semantics through Iyer lowering. So there's this contention here where Iyers try to be minimal and have the minimum number of nodes and cases in them, but the HDLs try to capture the actual design semantics. How do we pass this intent all the way from the HDL level down to the synthesis tool without destroying them in the process of lowering? And the high-level question is, if we could design some synthesis front-end from scratch, what are the semantics in the source level RTL or above that would be most valuable to preserve, that the synthesis tool would want to know about? What do we currently try to reconstruct in synthesis that would be much better represented if we could just pass it directly from the high level? The other question is like modules. What are they good for? Modules are used for three things that I can think of. One is like instantiating a circuit and stamping it out multiple times. One is to establish a parameterization boundary, and the other one is to add hierarchy, mostly for like the user experience. So I have these like analogies where we can try to treat modules as if they were functions in software, parameters as if they were function arguments in software, and hierarchy as being nothing more than a call stack in software. So with these things in mind, can we perhaps like infer modules from an HDL? Do we even need to define them explicitly? Or are they even a good abstraction? Right now, doing cross-module references or regrouping of modules is a big pain. Can we actually just remove the need for doing this? And finally, the most important point is like incremental elaboration is actually very important. So we've seen modern day build tools are very incremental in nature. So not only is the build done incrementally, but even the processing of the build description files is also incremental. And in a similar way, as these hardware generators grow, elaboration becomes an iteration bottleneck. We shouldn't elaborate the entire circuit even if just a small piece is actually changed. But in order to do this like run-to-run caching, we actually need analysis of the generator source code itself. We can't just memoize a function because underneath the hood that function might change. So how do we actually make this viable? And I think content addressable languages like Unison provide one potential answer in this direction. Can we potentially like use term level analysis and hashing in order to determine when a particular term has changed and when we have to invalidate its cache for the next run? So these are like summary of all the questions I talked about in this talk, and I'd love to discuss them with all of you coming up soon. So thanks.